In the second section of Chapter 15, we're going to focus on a new definition related to the term conjugate base. Conjugate bases, let me say plural, and acids. We'll also look at the strength of acids, writing an expression for Ka, which is the equilibrium constant for acids. Then we'll also look at Kw, which is the equilibrium constant for water. And based on this equilibrium, we will take a look at starting our pH calculations. In section 15.1, we defined an Arrhenius acid as one that produces hydronium. Remember that these two terms, H positive or H3O positive, are equivalent. So an Arrhenius acid produces hydronium in water. So we need to think about what's happening at the molecular level, starting first with the Lewis structure of HCl, shown here. So when we talk about ionization, we're going to produce products that are ions. In the last section, we looked at how electronegativity impacts the strength of the acid. So a way to think about this is how strong the attraction is for electrons. Strong attraction for electrons. So HCl, because that chlorine is electronegative, its Lewis structure, its Lewis dot structure on its own, remember there are 7 valence electrons. And so essentially what chlorine is going to do is take that other one with it when it dissolves in water. It's strong enough to pull that electron to itself. And so hydrogen is left without the electron, forming hydronium, and then we get the chloride ion, which has the 8 valence electrons. Okay, so in that way, we're forming ions. Very strong acids or bases have a tendency to completely ionize, to form the maximum number of ions possible. And we'll take a look at that in a couple of slides. Sodium hydroxide is an example of a strong base. Remember that bases, the Arrhenius base definition is that it produces hydroxides in solution. Okay, again, we can look at the Lewis structure. Sodium, being group 1, has 1 valence electron, and the hydroxide is a polyatomic ion in truth. Okay, so it has that negative charge. When we put these together, before the hydroxide becomes charged, okay, it's going to be seeking that electron, and we'll pull it to itself. Again, oxygen is a very electronegative atom. Okay, so we get the formation of these 2 ions, sodium positive 1 and the hydroxide negative 1. So all soluble hydroxides are strong bases. we're going to focus more on acids for the majority of this section. We need to add to our acid-base definitions and look at the term conjugate. Right, so a base reacts with hydronium. The Bronsted-Lowry definition of a base is a hydronium acceptor. And so here you have the base ammonia, and it accepts a hydronium from some other molecule to produce NH4 positive 1. So this ammonium is the conjugate acid of the base. So the conjugate acid is a base plus hydronium. And these are always going to be in pairs. That's a key term there. So you look at what it's doing on the reactant side and the resulting product to tell you if it's a base conjugate acid or an acid conjugate base. Let's define those a little bit more. They become important because of our discussion about buffers, which will be in Chapter 16. We'll get to that in a little bit more detail then. All right, so let's look at the example of the conjugate acid-base pair in the second example. The Bronsted-Lowry definition of an acid is a hydronium donor. So the conjugate base is the acid minus hydronium. All right, let's look at a couple of examples. We're going to continue with an example problem. Let's take a look at this reaction. C5H5 NH plus water produces C5H5 NH2 with a positive sign plus OH negative. Okay, so we're going to do the same thing. We're going to identify, and I can just connect the two different half reactions together, like so. So if I take a look at this first one, C5H5NH, it accepts hydronium. So that is my base. That means that the C5H5NH2 is the conjugate acid. Right, then when I look at water, water has donates hydronium. So that is my acid, and the OH negative, the hydroxide. Okay, let's be clear here. That's the base. That's the acid, and hydroxide is the conjugate base. In this reaction, when we write them, the acid and base will be on the reactant side, and the conjugate acid and conjugate base will be on the product side. They'll always be in pairs, so you want to look at the pair that has the same root. Okay. And so in this case, the bicarbonate, this here, is acting as a base. If we look at what's happening between the two sides, we can write the half reaction. goes to H2CO3. We have added hydronium. Okay, so that is a base, and this is the conjugate acid paired. And in the second example, we look at water going to OH negative. Water in the process here has had hydronium removed, and so it has acted as a donor, hydronium donor. So this is my acid, and this is my conjugate base. When we consider strong and weak acids, we need to look at a couple of clues to tell us that something is reacting completely. We know that there will be complete or maximum ion production. And that the arrow is only going in the forward direction. By definition, there are 6 and only 6 strong acids: hydrochloric acid, hydrobromic, hydroiodic, nitric acid, perchloric acid, and sulfuric acid. Out of the bunch, only sulfuric acid is a multiprotic or diprotic. This is something that came up in class on one of the problems. When you're looking at this diprotic acid, because it is a strong acid, we don't expect to see any intermediates. Okay, for example, the formation of HSO4 negative. That is not going to happen. It is going to completely ionize and produce 2 hydronium and 1 sulfate ion, because it is such a strong acid. So let's take a look at a conceptual idea of the difference between a strong and a weak acid. On the left-hand side, we have a graphic to represent HCl, and on the right-hand side, HF. And think about the periodic table in group 7A. Fluorine is the first element, then chlorine, then bromine, then iodine, and acids increase in strength as we move down the periodic table. Okay, so we know that HCl is a stronger acid than HF. We can represent that looking at the 2 different beakers here. When HCl dissolves, we have complete ionization, so we'll just say all ions possible form, and there's no molecular HCl left in solution. So if I'm looking at the chart here, I see that we've got 1, 2, 3, 4 hydronium and 1, 2, 3, 4 chloride. So hydronium is equal to chloride. Now if we look at the other side here, we have HF. When HF dissolves, it will partially ionize. So we will still have some molecular hydrofluoric acid. And so taking a look at that, on my negative charges, I see 1, 2 fluoride ions and 1, 2 hydronium, and then I still have 1, 2, 3, 4, 5 hydrogen fluoride. So if I think about that in terms of an equilibrium, we have HF goes to hydronium plus plus fluoride. Okay, and this, I should have a double arrow here to indicate equilibrium. We could write this Equilibrium is Ka. A just means acid, and that is hydronium times fluoride concentration divided by HF. And I could actually put in numbers here if I wanted to, because we have that on the chart here. So Ka, I could just plug those in. How many hydronium? Those are circled in blue. That's 2. How many fluoride? Also 2. And then how many HF? That is 1, 2, 3, 4, 5. So we have 2 times 2, which is 4 fifths, or 0.80. So we could actually solve for that equilibrium value. So Ka just means equilibrium constant for an acid. Ka's are considered constants, and so we have this chart here. We'll look at a couple of examples in just a moment. But first I want to talk about what I would call a generic acid-base equilibrium reaction. That's really terrible. Let me erase that. Okay, and redraw that. H positive plus A negative. All right, A just stands for A is equal to an acid. It's just a generic term. And so this is my acid on the reactant side, and the conjugate base is the A negative. I could write the equilibrium. Ka is equal to hydronium concentration times the concentration of the conjugate base over HA. We're going to look at some calculations with this particular version of pH formulas. It's called the Henderson-Hasselbalch. And that's some of the problems that we'll do in Chapter 16. But in the meantime, let's take a look at 2 different acids here. All right, and I'll just pick a couple. We'll look at 2 that are right next to each other. Hydrofluoric acid and formic acid. We already know the reaction of HF. It's hydronium plus fluoride. And we're told that Ka is equal to 3.5 times 10 to the negative 4th. And then we can look at formic acid. We've got the reaction here. So we could write our Ka expression for that one. The products, and I'm going to write H positive instead of H3O. It's just less writing. That's all. CHO2 negative over HCHO2. Remember, we do not include pure liquids or pure solids, and so the water liquid consequently is not in the equilibrium expression. We're told the value for this is 1.8 times 10 to the negative 4th. So the question is, which one is the stronger acid? And the way that I do this is to compare the Ka. The larger Ka means the stronger acid. All right, so if I'm comparing these, I can convert them to standard notation. Sometimes it's easier to make the direct comparison that way. So 3.5 times 10 to the negative 4th and 1.8 times 10 to the negative 4th. So I can look at these side by side, and I see that this is the larger number, which means HF is the stronger acid. Okay, so we can answer our question there. And generally speaking, I don't have to go through that direct comparison each time. If I just go up the chart this way, it increases in acidity as we go up. So as we go up, it gets stronger acid. Okay, we're going to switch topics here and talk about Kw, which is the equilibrium constant for water. So A is acid, W is water. It's really not any more difficult than that. Water can act as an acid or a base. And notice we use the Bronsted-Lowry definitions here. All right, so if I'm writing the equilibrium expression, remember we're not going to include the pure liquids. We're only going to include the two ions, okay, shown here on the product side. I would write that Kw is equal to hydronium, and I'll just write the shortcut version of that, times hydroxide. And this is in fact a constant. 1.0 times 10 to the negative 14th. And this is where the pH scale is based on. It's a negative log scale, so what that means is we're taking the negative of the negative. So the pH scale is a positive scale, and it goes from, log just means we're looking at the exponential value here. The pH scale goes from 0 to 14. I know that the product, when I multiply these two together, always equals 1 times 10 to the negative 14th. So I can solve for an unknown if I know what that value is. Let's look at a couple of simple examples here. If hydronium is equal to 1 times 10 to the negative third, what is hydroxide concentration? All right, so I just plug and chug here. Kw, I'm told, is 1.0 times 10 to the negative 14th. I'm told hydronium, which is 1 times 10 to the negative third, and I do not know what hydroxide is. So I'm going to divide both sides by 1 times 10 to the negative third. Okay, those cancel out. Because these numbers here are the same, 1 and 1, they're going to divide to equal 1. And so I just really need to look at the two exponents, negative 14 and negative 3. And our exponential rule says when we divide, we subtract. So if we divide, we subtract the exponents. And I can only do that if the numerals associated with them are 1 or the same thing. All right, so this would be negative 14 minus a negative 3. So in other words, negative 14 plus 3, that is negative 11. So without doing any hard calculations at all, I know that hydroxide is equal to 1 times 10 to the negative 11th. And I can tell that this is an acidic solution. I can look at the exponent of hydronium concentration. If it's less than 7, it's acidic. That's really terrible. Let me erase that real quick. Less than 7. Then it's acidic. And so when I look here at my hydronium concentration, I see that it's a 3. So this is going to be a pH of 3. And I'll show you how to make that assumption in the next video. Let's look at a couple of example problems. In the first one, I've got 4 different acids, and we're going to identify a strong or weak. If they're weak, we're going to write an expression for Ka. Right, so let's write these down first, then we'll talk about each one. Number 1 is HNO3. Number 2 is HCl. Number 3 is HBr. And number 4 It's H2SO3. Right. To identify something as strong or weak, remember I'm going to look back at the chart that had my list of 6. And you can go back and take a look at this. But nitric acid is on there, hydrochloric acid is on there, and hydrobromic acid is on there. So those 3 are all strong acids. If we look at number 4, this is H2SO3, not H2SO4. Remember, this is called sulfurous acid, and it is a weak acid. All right, and so we could write this in equilibrium. We'll go ahead and just do one proton removal here. Okay, that's another difference between strong and weak. We're just going to take off 1. So there's my negative plus hydronium, and these are all AQ. So when I write Ka, it's going to be the products, HSO3 and hydronium over H2SO3. So that is my expression for Ka. I could find out where it is by, looking at a reference table as far as how strong of an acid it is. In our second example problem, we're going to use Kw 1 times 10 to the negative 14th and solve for hydronium or hydroxide, just depending on what we're given. And let's look at 3 examples. Number 1, hydronium is equal to 1 times 10 to the negative 5th. Number 2, hydronium is equal to 1.2 times 10 to the negative 8th. And number 3, let's do hydroxide this time. Hydroxide is equal to 8.5 times 10 to the negative 5th. All right, so we're going to plug and chug these problems. Whatever one it is, let's see, if I'm solving for hydronium, it's 1 times 10 to the negative 14th divided by hydroxide. And if I'm solving for hydroxide, it's 1 times 10 to the negative 14th divided by hydronium. Okay, so that's easy enough. Let's look at number 1. I'm told what hydronium is, so I want to know what hydroxide concentration is. That's 1 times 10 to the negative 14th, that's my constant, divided by my given, 1 times 10 to the negative 5th. Okay, here, these are the same number, that's the same, so I can just do my exponent rule, hydroxide, and that would be negative 14 minus, whoops, let me erase there. Didn't mean to quite go that far, but let's see. 10 to the negative 5th. Oops. I'm just messing that all up. Let's just rewrite that here. 1 times 10 to the negative 14th divided by 1 times 10 to the negative 5th. And so this becomes negative 14 minus a negative 5. So hydroxide is equal to 1 times 10 to the negative 9th. And I can tell that this is an acidic solution, okay, because hydronium is 1 times 10 to the negative 5th. And remember I can look at the exponent on hydronium to tell me what the pH would be about. In this case, it is 5. That's less than 7. And so this is acidic. All right, second example. This time I'm going to have to actually plug and chug it. All right, I'm looking for hydroxide here. I have 1 times 10 to the negative 14th divided by 1.2 times 10 to the negative 8th. And I have to put those exponentials in, remember, using my EXP or EE button on my calculator. When I do that, I get hydroxide is equal to 8.3 times 10 to the negative 7th. It should have the same number of sig figs as the given. There it's shown to have 2. All right, I know that this is a basic solution because I'm going to look at the exponent of my hydronium, and in this case it would be somewhere between 7 and 8, and so it is mildly basic. Right, in our third example, we're solving for hydronium. That's equal to 1 times 10 to the negative 14th divided by 8.5 times 10 to the negative 5th. So I go ahead and put that in my calculator, and I get 1.2 times 10 to the negative 10th. And when I look at that exponent for hydronium, it's a 10, which is higher than 7, so this would be a basic solution. Next time we'll do a couple more calculations with hydronium and hydroxide, as well as go through all of the pH calculations.